What if you didn't have to commit to a number of clusters at all? Not up front, and not even at the end. What if, instead of a single answer, the algorithm handed you the entire family tree of your data, from every point standing alone all the way up to one giant group, and let you choose the level of detail after seeing the whole structure? That is precisely what hierarchical clustering gives you. And the picture it produces, a dendrogram, is one of the most readable summaries in all of machine learning. Let's dig in. So how does hierarchical clustering actually build that tree? The most common version works from the bottom up. Follow it one merge at a time. Start at the very bottom, where every single data point is its own tiny cluster of one. Nothing has been grouped yet. If you have 1,000 points, you begin with 1,000 clusters, each one waiting to be joined to its closest companion. Now find the two closest clusters anywhere in the data and merge them into one. That single merge is the whole engine of the algorithm. What counts as closest depends on a linkage rule, but the move is always the same. Locate the nearest pair and fuse it. Repeat that merge again and again, each time joining the next closest pair, and record every join as a branch in a growing tree. The height of each branch marks how dissimilar the two groups were when they merged. So tight, similar clusters join low down, and very different ones only join near the top. Keep going until every point sits under one single root, and you are left with a full tree called a dendrogram. Now comes the payoff. Draw a horizontal line across it at whatever height you like, and the branches it crosses become your clusters. Cut low for many fine groups. Cut high for a few broad ones, all from the same tree. So why reach for a whole tree instead of a single flat answer? Here's the contrast, side by side. Think about the usual flat approach, like k-means. You commit to one fixed number of clusters, and it hands back exactly that, a single partition, every point dropped into one group, with no sense of how those groups relate. Want a different granularity? You rerun the whole thing with a different number and hope. Hierarchical clustering hands you the entire tree instead of one slice of it. You see how points nest into small groups into larger ones, all the way up, and you pick the granularity afterward by choosing where to cut. One run captures structure at every scale, and the dendrogram makes it genuinely easy to read. Strip it all down, and three ideas make hierarchical clustering work. It builds a tree from the bottom up. Every point starts alone. The two closest clusters merge over and over, and the record of those merges becomes a dendrogram, a branching picture whose heights reveal how similar the groups were the moment they joined. A linkage rule defines what closest means. Single linkage uses the nearest pair and can chain. Complete linkage uses the farthest pair for compact groups. Average linkage uses the mean distance, and Ward's method minimizes within cluster variance, which is the most popular choice by far. You cut the tree to pick granularity. Because the full hierarchy already exists, choosing the number of clusters is just deciding where to slice. So you never fix a number up front, and you can explore the structure at every scale from one single fit. All right, let's lock in what matters. Hierarchical clustering builds a tree of nested groups instead of one flat partition, so you can choose how many clusters you want after seeing the structure. The common version starts from the bottom, every point alone, and repeatedly merges the two closest clusters, recording each merge as a branch of a dendrogram. A linkage rule sets what closest means from single and complete to average and Ward's method, and cutting the tree at a chosen height picks your granularity without ever fixing k. Its main cost is speed, since the classic algorithm scales poorly to millions of points, and early merges can never be undone. If untangling machine learning this way appeals to you, There's a whole library of it waiting at standarity.com. See you there.